Good morning, good afternoon, good evening. You are with David D. Hilser, and this is Saturday Science Chats. That's right. This is David D. Hilser, of course. Let me bring that up. I am your host today for Saturday Science Chats, and we are sponsored and run by the John Chappell Natural Philosophy Society and Dissident Science. I want to welcome all my subscribers. Hey, past 3,500 subscribers. That is great. Welcome everybody from Dissident Science. And also, we're approaching 800 subscribers on our YouTube channel for the John Chappell Natural Philosophy Society. And let's talk about all that. Today we got a great show, of course. We have Glenn Borchardt going to be talking about the infinite theory, universe theory. So let's go forward. Like I always do, a little bit of presentation of who we are, what we do. Again, oh my goodness, sorry about that. But we are the Saturday Science Chats, and we are sponsored again by the John Chappell Natural Philosophy Society. It's been around for a couple of decades now, maybe going on its third. It's in its third decade. It used to be the Natural Philosophy Alliance, and Dissident Science is my YouTube channel. The CMPS's mission is to be an organization that, above all, promotes critical thinking without malice, to be an organization that supports, publishes, and promotes serious scientific work outside the mainstream, to provide a forum for open debate about modern topics in physics, cosmology, philosophy, and mathematics, and to provide a forum for presenting serious papers, theories without fear of censorship, to be run and controlled by its entirety by its paid memberships, including the election of its directors by its members. How can you participate? Well, you can sign up on naturalphilosophy.org. You can become a member. Memberships are annual. I want to thank, we have some new members out there. So I want to thank some of those members who are paying their annual dues. It is essential. It is vital to, vital meaning it is our lifeblood. We don't exist. This Saturday morning chat doesn't exist. These things aren't free, these kinds of services that you see. So it's very important. And I really, really appreciate the people in the last months who've been coming through to pay our bills. We've got, I think, $700 this month for the hosting of our website. And there's all kinds of other software that we use today. And that's the way it is. It's all subscription based. You can participate in our community discussions on our website. And you can also, of course, post news about us on social media, because that's really where things happen these days. Our websites are, there are a number of them. The community website is naturalphilosophy.org. That's where you can meet our community of scientists and critical thinkers and interact with them directly. It's easy to sign up. It's a great website, a new website using Buddy Boss, and absolutely great, fantastic software. And we have a lot of discussion groups and threads you can follow there, and post stuff, things that are interesting. It's sort of like Facebook, but it's also got forums and all that kind of thing. And we also have our our online magazine, sciencewoke.org. If you don't know there are problems in science, you're going, yeah, right, Dave. Big Bang, relativity, those are all, they teach them everywhere. They must be right. Well, guess what? Just like many things we've been told in our lives in the last 3 or 4 decades, it's not always what the news tells us. And that's the same way in science. So if you want to become more woke, and I guess people get all upset about that word. We even have some of our scientists don't want to be included because they don't like the word woke. Well, woke means just woke up, to be able to look. Your eyes are open. So we use it. We don't have any malice toward that word. So anyways, it's just mean to be eyes wide open with science. And of course, we have our Wikipedia, which has over 10,000 pages, and that gets indexed quite a lot on Google. So if you are one of the critical thinkers whose profile is there, and you want to get more profile in your work in there, you should, because many people, if you just Google their name, the page that comes up is our Wikipedia page or our Science Woke page. Just try it out. And of course, we have, coming in 2021, we're going to have our first professors, our first teachers writing courses in our Chappell University, where we'll have courses in natural philosophy. And if you are interested, contact me, because we're going to have, starting in January, we're going to have regular meetings online to discuss or the university and what we want to do with those things. So you can be a part of that. Here's our community website, naturalphilosophy.org. Natural philosophy being the word before physics and cosmology. And you can see this is just grabbed from today. Got quite a few members. Those are the recently active members. And there you can just discuss. You can go in there, register, and of course you can pay again if you have the ability to do so to keep this organization running and all its software and websites. And this service, StreamYard, which costs, I think, $200 a year or something like that. So always appreciated of people. And now we're going to get into Critical Thinker Science News. I always watch the science news, and especially those people from my dissident science channel know I really look at the news, and I'm not always fond of it. So let's take a look of what the headlines are. If you go to Google, you can click on science and then click on physics, and that's where I get these. So you should try it out. But we're going to look at this article a little bit later on, but it's sustained fidelity quantum teleportation achieved for the first time. Quantum teleportation. Now, I can understand quantum teleportation. Oh, that's everybody knows that. We do that all the time, everywhere. Well, I'm being obviously sarcastic, but it's the sustained high fidelity part of it it's important, I guess. But you can see that's in the headlines a little bit. We also have exotic hyperons interact with protons at CERN. There's more the particle zoo, where Alexander Unziker talks about particle physics as being basically a bunch of arbitrary attributes with arbitrary packages with arbitrary attributes. So that is something that is always, to me, amusing. The Milky Way's primordial history and its fossil findings. Of course, you always have that. We're going to be talking about with Glenn Borchardt today, and he is. Obviously talks about the Big Bang and the infinite universe. So this idea that all of our universe exploded out of this little point is a little bit. Most of us outside of mainstream just don't buy that. It's an eternal universe, both in time and space. Many of us subscribe to that. And of course, there's gravitational waves, probe exotic matter inside neutron stars. It's really quite amazing how we pile one thing up after another on another. Gravitational waves. We don't know they don't know what gravity is, but they say it's there and there's waves. Prohibit exotic matter. I mean, come on. If you're talking about exotic in science, then that means basically you don't know what it means. Inside neutron stars, and again, we talk about all these things, but our particle, the model of particle physics and the particles in the universe, we are, as Alexander Unziker says, you can throw away most of those from 1930 on. Just throw it out. Researchers created entangled photons 100 times more efficiently than previously possible. I think these are all different headlines to the same thing. Clickbait. We call that in the new media, social media world, clickbait, which it sounds bad. It is bad. Of course, let's take a look at this one. Researchers have achieved sustained long-distance quantum teleportation. The breakthrough made by researchers at Caltech, Fermilab, and NASA, among others, is a step towards practical quantum internet. Now, this is where you get science and all the hype of things that are just ridiculous philosophically, like quantum mechanics and quantum. It gets thrown around because why? Because people are clickbait. It's basically what it is. It means they're sensational. For those of us who are older, the sensational headlines. And of course, if you say Caltech and Fermi and NASA, oh my gosh, this has got to be right, because all those people, I mean, they've got to be right? But let's take a look at the headlines, and I think we get a little bit more insight into this. I'm in computer science and quantum computing and all that. I know somewhat about. In a major breakthrough, the quest toward the quantum internet, a technology that would revolution computing in a myriad ways. Sure, they always say that. No matter breakthrough, it's going to change the world. It's a consortium of well-regarded institutions. You notice all this. I mean, this is just a way of saying, okay, we've clickbaited you in. Now we're going to tell you that all the authorities that are here are all right. If you don't understand it, I'm sorry, little boy, little girl, you are not capable, and you need to be, you can be indoctrinated, as we say in the university, and then of course you'll be accepted. Caltech, look at that, Fermi, AT&T, Harvard University, blah 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 blah. Okay, so it's just talking a lot about who. And whoops. Here we go. Sorry, went too far. Now we're at the. I don't know how I went too ahead. Here's what quantum teleportation does not involve the actual transfer of matter. Isn't this bizarre? Now you see the game that they play in the journalists, the science journalists. They're not science journalists. People aren't interested in science. I get literally emails, a couple of emails every week asking to write for our magazine, Science Woke. And it's all from these people who are these factories of people who write articles that if you've ever been to those websites now, all these articles that look interesting, you click on, you can hardly read the article. You can't tell the difference between the article and the two-headed babies from Mars, clickbait on the side. Well, that's just a big thing to sell, people on just like old tabloids. And so what you do is you get them in, you click on them, then of course you get to the real stuff. And they got a disclaimer: quantum teleportation does not involve the actual transfer of matter. Well, why do they use it? Well, they use it because it's sensational. So it says, rather, quantum particles are entangled, dependent on each other, even over long distances. Now, infinite universe theory with Glenn Borchardt, he is a person that we talk about. Everything affects pretty much everything. But this is not what they're talking about. So, in a way, entangled particles behave. Look at that. In a way, what does that mean? In a way, sort of like, well, maybe entangled particles behave as if they were aware of how each other particle is behaving. Now, again, this is all these people are working with all of this without any model for light or gravity or magnetism or any of that. And until we get a model for any of this, then why do we even bother? Well, again, this is the way it works. So I'm going to go on. You get the idea. Quantum, they're using quantum computing. It just all it means, what all it means? All this is, I'm computer science. Here, I'll put it in a very succinct way. What is quantum computing? It's not using zeros and ones. It's using something more ample than the zeros and ones, off and on. That's it. That's all it is. And of course, if you only use zeros and ones, you have a lot of computation. So you have to make incredibly fast, incredibly large, incredibly dense circuits so that you can deal with all this stuff. If you have quantum, what's going to happen? It's going to relieve a lot of that. And so you can be able to do calculations, and you can store information in a way where you can store it in much more compact form, and you're not dealing with just turning on and off switches. That's basically, our entire world in computers is still turning on and off a switch and the states of those. So that's the only difference there. And then so they use quantum, and then they love it because they're in the news. If you're in a university in the middle of Ohio, and it's a small university, you want to put Einstein in it or put quantum in it, and next thing you know, you're news. Okay, so let's keep moving forward. So let's take a look at some more news. Unsucker's Real Physics. Again, if you have not subscribed to his channel, you should. It's called The Machian, for Mach, I guess. And he's been putting out some new videos. This is about Steve Weinberg. He's telling you about whether or not, he's telling you a lot about the fame and, are people hyped or are people for real? Are these people that people are saying are great? Are they really great? Or in fact, is it just a bunch of hype? So you want to check that out. Alexander Unsucker has agreed. I talked with him via email. I've interviewed him numbers of times to come on the show, on the Saturday morning chats, and be interviewed and have some conversation with him. I love conversing with him. He is just an amazing mind, constantly thinking about it, about physics and cosmology as a critical thinker. So you don't want to miss him. Of course, we have this week again. This is our week. So Kashmir Force. If you haven't, Rayfleming, you can see his subscribers slowly going up. He's had his channel a while, but he's really starting to do a lot more videos. He has more of a lecture series videos where you can read about. But again, it's really interesting, thought-provoking. Again, you don't have to agree with any of these people that I'm showing you. It's more of just thought-provoking, thinking outside the box. You're always going to learn something, even again, if some of it you're not agreeing with. So another person is Lauriegardee, the fractal woman. She passed me, man. She was down there for a while. I was talking to her a little bit about the, how to grow her community, and she passed me. She's like 4,000, 4,200, almost 1,000 more subscribers than me. But I tech and I do things that are a little bit more controversial. So I would imagine it's a little harder for people to stick to the dissident science channel because of that. But she really has put a lot of really great videos. You can see these on board. I should have gotten a better screenshot, but if you go to her latest video, she's talked a lot about relativity, and that's really interesting. So you want to check her out. She is a member of our organization. Jeff Yee, of course, has this contest going still. You have to check out some of his videos have quite a lot of views, but the energy wave theory, really amazingly detailed theory. I checked that out. And again, subscribe to all these people. You don't have to, Rayfleming, he needs subscribers, folks. Why? Because the more subscribers you have, the more that you get in the algorithms of YouTube to be shown to somebody, and we get more people in our direction. And anybody who's out there trying to make critical thinkers, that's really important. So I know maybe the people who are older, like myself, 60s and over, I don't care, Facebook is a waste of time. No, it's not, folks. Guess where everyone's coming? We have new members here. We have people watching today for one reason and one reason only. They found us on YouTube or Facebook. So that's where communities are. We're talking about billions of people. We're not talking about millions. Talking about billions. So get it through everybody's head that this is the way the world works today. And that's great because it allows us to get our voices out there. But you got to subscribe. Show them some love and some vital support as one of the YouTube channels for SpaceX, which I like to watch. He says, "You rock." So you guys rock. Keep up your support. Particle Guru, my dad, he's almost to 400. My goodness, last time I showed this slide, he was like, no, he's going up very slowly, the turtle. But he talks about a lot of interesting topics related to the particle model, which, by the way, follows the neo-mechanical model and rests squarely on the shoulders of Glenn Borchardt's work. And the Nick of Time, another person we have that's going to be coming up and talking with us about special relativity. Check out his YouTube channel. It's got a lot of great videos about relativity. This guy is a real critical thinker. I think he's from Harvard, and he is definitely worth his clicking on and watching. And he too will be a guest on the show in 2021. Gee, I can't even say that. It's so scary. I thought 2000 was bad. And of course, as Alexander Unsker says, keep working on your passion. Don't give up. Yes, we don't agree with each other in a lot of things, but we all need to just keep working. And the people's work who is influential will influence, like Glenn Borchardt's work, which has influenced a lot of new models out there. So that's quite important. So keep on working, keep working on your passion. I finally fix that phrase. So that's the Critical Thinkers Science News for today. So I hope you enjoyed that, because I think nobody's doing that, and we should do that much more. Okay, so we're going to be bringing up our guest today, but I see him there. I don't see video for him. I see him sitting there lurking, but he is the person who has written a theory called the infinite universe theory. We're going to be talking to him today, Glenn Borchardt. Okay, I see him down there. He is here. I'm going to try to unmute him. Hey, Glenn, are you there? Or we may be having trouble. Maybe he is in California and he is
How's
his, are
that?
you, hey, how you doing?
Okay, and start the cam. Okay, there you
Oh, there he is.
Yeah. Well, thanks for
Oh,
having me on, David. That's great. We need to talk more about infinite universe theory. That's partly because there's so much of it to talk about.
yeah, there is. There's absolutely is. How's your weather there? I was worried that I didn't see you. You were like hibernating there. I get pictures, I think, from your wife of beautiful snowstorms
Oh
there. I
yeah,
mean,
right. Yeah,
it is just gorgeous.
we're locked down in a wonderful place, Tahoe, California. So
Oh,
it's been unfortunate that we're locked down here and quarantined. And of course, the southern part of the state is maxed out. There are no real beds available for the
right.
pandemic, so it's really sad. And we had many deaths here. We used to have one death in the county, and that was for months and months. And now we have 38.
Holy cow. It is quite amazing.
Yep.
We had set up a time for actually we bought tickets for California because my dad's 83 wanted to see his son, my brother who lives in Pasadena, and then drive over to Arizona. And we got those tickets well over a month ago. Pretty good price. And then when we started contacting people, they said, "Don't come." So we ended up having to get a voucher for it, and it is how do you say when you were like muted in your I think did Glenn get COVID? Uh,
No.
but it is raging out there, unfortunately, and the death toll, all the comparisons with flu doesn't kill this many people. So obviously this is different. But the good thing is we have this kind of medium and allows us to communicate and work with each other. So I didn't go. I had a lot of stuff about you. I think people are getting to know about you. But today's going to be really fun, Glenn, because you sent me some slides. We're going to be working next year on getting a course done, and of course, Glenn Borchardt is going to be one of the teachers there and putting together a course. But I'm going to make this fun because there are some things I'm going to challenge Glenn on today, but they don't, it's not on the infinite universe theory. It's just on the interpretation of his own philosophy. So let's get to some of the slides I put together. I put together stuff. So let's just look at the conclusions, right? I thought this would be interesting right away. What the conclusions, what we're going to be looking at today. It's sort of like a summary. Maybe talk about this. This is one of the slides and this will sort of set it up for our discussions because sometimes they don't go in a linear order. But I got a bunch of slides after this. I decided to put this. So, Glenn, maybe you could walk through some of these.
Okay, well, conseponability requires infinity. Now, conseponability is a word invented by Collingwood in 1940, and it means that if you can assume A, it can't contradict any other assumptions that you have. And of course, in science, we have to have assumptions. One example is that as scientists, we believe there are causes for all effects. That's an assumption. That's a faith that you can't prove that. There are an infinite number of causes, of course. So until you prove all of them, you haven't proven it. But we've done billions of those experiments, and we still believe, and I have always believed, that there are causes for all effects. So conseponability requires infinity. Now, if you use finity, you have a problem with that. And if you study my 10 Assumptions of Science book that I wrote in '04, and of course, I include that in Infinite Universe Theory book that we're going to be talking about. You have to be able to have conseponability, and what we say is that there are an infinite number of causes for any effect. What does that mean by infinite? Well, the universe is infinitely subdividable. So that means that the macrocosm, that is the environment of a thing, a microcosm, is going to have an infinite number of things. And so you can never get for our second assumption, which says that there's uncertainty, that you can never get a perfect answer like Einstein demanded and Newton demanded. They're believers in infinity. so that you have a finite number of causes for any effect. Now, mostly the causes diminish with distance and with size of particle and so on, but nevertheless, there are an infinite number of causes for any effect. And that, then of course, our assumption of infinity says that the universe is infinitely small, has subdividable, and infinitely integratable. That means it goes on and becomes essentially units that are, remember, we have the solar system, we have the galaxy, and then we have clusters of galaxies and superclusters and so on. And that's what the universe is like. And of course, there is an ether. This is one of the things that is very important here. Our basic theory is univironmental determinism. That is, what happens to a portion of the universe is determined by what's inside it and what's outside it. This applies to everything. It applies to you. What's going to happen to you and me is determined not just by you or me, but by the environment in which we exist. So time is motion. This is something that people have resisted forever because Einstein has totally messed this up. He thought of motion as being a thing, a dimension. It's not. Motion is what things do. The universe consists of matter in motion. So matter exists. Matter constitutes an XYZ portion of the universe. And it's always in motion. Every part of the universe is in motion, of the infinite universe. In particular, it's not expanding or anything, but it's just moving from here to there. And now I say light is motion. Light is not a thing. That's what Einstein's, one of his major mistakes was to consider light a particle. It's not. It's motion of particles. It's sort of like sound. Sound is the motion of particles, mostly nitrogen in the atmosphere, moving hither and yon. And the sound is a wave that moves through the atmosphere at about 343 meters per second. Light does the same thing through ether. Now, there are people who say, oh, there's no ether and there's empty space. Yes, that is true for the Big Bang Theory and for those who believe that there could be empty space, which there is not. No one's ever found that. And of course, gravitation is a push, not a pull. And that is related to the whole idea that there's ether, which has different characteristics depending upon where it is. And a little bit later, we'll probably get into that discussion of how ether produces gravitation. Well, I'll just summarize it here a little bit. Everybody knows, or most people know, that gravitation is an acceleration. Okay, if you're going to have acceleration, you have to have an accelerator. You have to have an object, a microcosm, colliding with another in order to accelerate it. And that's the whole idea, that gravitation must be a pull. There's no such thing as attraction. Sorry about that. And of course, the universe is three-dimensional and infinite. Now, that's really important because it is the last cosmological revolution. Remember the various ones we went to, Copernicus and so on. And that is going to be so important that we finally realize that the universe is infinite. It goes on and on and on, and there's no reason for it to end.
Yeah, I thought it was a good way to really sort of summarize, because I've got some other slides talking about exactly these things. So I thought we would be able to move forward. I believe this is your website as well, right? For those
Yeah,
people
right.
interested.
Yeah, you go there and find out various things, and you can find out what books we have, and you can find what interviews we've had and other details. And there's a hookup to the blog that we have.
Yeah, exactly. The blog's really great. I highly recommend people subscribing to that. So let me go forward here. Um, Here we go. So I'm going to give you the questions here and make them nice and easy and big here. There you go. The first one: define infinite universe theory.
Okay, well, you can't define anything that's infinite because that's fine is fin, it means that there's an end of some kind. But we can give a description of it and what it means for us. If the universe goes on and on, we have 13.8 billion light years worth of galaxies. Actually, one estimate was 2 trillion galaxies.
That'll
400,
keep going up.
yeah, and there's 400 billion stars in our own galaxy, and there's 2,000 of these, 2 trillion, excuse me, of these galaxies. So it's just amazing. That's what the universe. So it goes on and on, and it always existed. And I have a nice little anecdote in one of my books, anyway. I was studying earthquake history and so on, because you don't know about what earthquakes occurred unless you study letters and documents, so on. So there's this little story about a priest who was trying to convert a native in California to say, well, the Earth was created, whatever, 6,000 years ago, or whatever he chose to tell him. And then the native said, the universe was created? It's you silly man. The universe has always been here. and that's quite profound, and of course he had to change his mind later on when the whips came out, but he actually was very wise in saying that. And of course he's only on the Earth really is 4.66 billion years old, and as everything is in the universe, everything has a beginning and an end. So that's why one of our assumptions has to do with complementarity. It says that all things are moving toward other things, and other things are moving toward them. So that's essentially, it's the opposite. Why we say it's complement is that it's the opposite of the second law of thermodynamics, which says everything is coming apart. And lately that's gotten another big press coverage, heat death of the universe and so on, that's expanding. So anything that's finite, if the universe was finite, it would have a beginning, right? And it would have an ending. But it's not. There's always something there, always something outside. So the cause for any particular event is always coming from somewhere else. And so that somewhere else is always present in the infinite universe. And this has profound meaning for our lives, and what we only have a few microseconds to live on this planet, and we're not going to be living anywhere after that. And so you better use your time wisely. Don't mess around.
Yeah. I think it's really interesting when I describe sort of the infinite universe to people. I say, look, let's just say there was a particle that the whole universe was made out of, right? That's the goal always. I mean, that's why we went from atomic structure, then we went to, protons, neutrons, electrons, that made everything up. And then someone in the 60s says, oh, I'm going to make up a word, quark, which was a quirky word on purpose, and everything's going to be made out of it. Of course, and then immediately there were 9 of them, and then the flavors started coming. And the idea is that if you were to have a finite universe and a finite particle that everything was made out of, it'd have to organize itself magically. I mean, how would it get to all this complexity by itself? It just doesn't happen. And when a person thinks about it, they go, yeah, that's sort of right. And when I confront people who have the ultimate particle, because there's quite a few critical thinkers out there who have their own model, and their goal is like everything's made out of this. One of them is ether. A lot of etherists think that, actually. And, when I said, okay, but how do they organize? What is the cause? And with the infinite universe, there's always a cause. Well, why do, the one question is, why do atoms organize themselves in such a structured way? Whereas, it looks like around where we live, all these planets and suns seem to be more chaotic. Well, the answer lies below it, right? The answer lies what makes those things up, and that characteristic. So it's just on and on and on. But the infinite universe theory finally gives us the answer that gets us away from like that problem of why, the cause and effect of things. Why are things the way they are? And it can't come down to magic. And the only thing you're literally left with is infinity. And it's got its own uncomfortable parts, right? I mean, infinity in emotional sense has sort of its uncomfortable parts where you think it just keeps going down and down and down. That means in my finger, there's just an infinite amount of things going down in there. It's sort of but there's a physical location in 3-dimensional space for all of this stuff, correct?
Yeah, right. And no two particles, no two microcosms, as I say, are identical.
Yeah.
And if they were, suppose these people with the finite particle theory,
Right.
all their particles are identical because they have no subparticles inside them.
Yeah.
They
Yeah.
don't have, yeah, the ingredients are solid matter. So remember, in all of this, we talk about the empty space solid matter continuum. The empty space is an idealization.
Yeah.
It can't occur. Idealizations are just imaginings, and no empty space has ever been found. And likewise, solid matter. There's no such thing as solid matter. So what is the actual universe like? It's the combination of these two things. Everything consists of what we think of as empty space and what we think of as solid matter. Now, empty space is simply matter that is less resistant to motion of other matter. That's all.
Yeah.
And
Yeah.
that's what empty space is.
And the
It's
way
not
I
really.
look at Yeah, I look at it as we're sort of in our unicosm, right? We're here, and for our perception, it'd be like seeing a fractal and all its details down to forever. We don't see that. What we see is we have a resolution. It's sort of like we live in a resolution of the universe. We perceive that resolution. We don't see all levels, all the way
Yeah,
down or all the
yeah.
way up. So. Okay, I've got another question for you. Here we go. Define, these are Dave DeHilser student questions for the professor. Define the difference between the infinite universe theory versus neomechanics. Oh, let me ask you, has anybody ever asked you that?
Oh, not really, because Infinite Universe uses neomechanics, and so
Okay. So maybe
uh,
if you could clarify that, I think that would
yeah.
be
So
that's
what's
the reason I'm asking.
neomechanics? Okay, you know what mechanics is. Newton's three laws and so on, and what neomechanics is. And by the way, I removed the hyphen because it's more accepted by me anyway. Anyway, neomechanics is essentially including infinity. And you can only do that once. And once you include that, you have an analysis of the world that involves matter and its motion. And that's what neomechanics is all about. And so, hey, you really changed. That's great.
Oh no,
Anyway, yeah.
it was never there. I'm kidding.
There you go. There you go.
What are you
Yeah.
talking about? That's in
Yeah.
the past.
Great.
Past doesn't
So
exist.
neomechanics is just simply talking about the interaction between microcosms and their environment. And remember, that's unienvironmental determinism. Go back to that. What happens to a portion of the universe is determined by the inside and the outside. You see how that fits with the infinity and with the infinite universe? Every little thing has to have an environment. It can't exist in empty space all by itself, like the Big Bang folks are trying to say. It's not possible. But of course, this has to do with philosophy. And if you want to, you can say just the opposite, and people do. And that's why we still have the Big Bang theory, even though it's terribly absurd. See, now when you talk about the universe exploding out of nothing, that doesn't make any sense to me at all. And how I say the universe goes on and on and on, and it's infinite and it's eternal. Does that make sense to you? Well, it's a little difficult, one step, but you have a choice. Either that or the explosion of the universe from nothing. Which do you want? Which do you prefer? Which will get you the best answers to all the big questions? And I don't think it's the Big Bang. As you can see, there's all kinds of problems with it. And if you look on, okay, let me hold up this book here. There you go. And you've shown that too. And I wanted to go to page 63 here, and it's about falsification, contradictions, and paradigm disproving the Big Bang Theory. Now, David, I don't know if you had decided to, I guess I didn't maybe send you that, but I was thinking about maybe reading that. Now, that's going to take a little while. You want me to do that a little later or no?
You can do that now. I don't see a problem. Because we do have the time. I've got other things we're going to be talking about, but we have time.
Yeah.
Go
Okay.
ahead. Go
Well,
ahead.
this is just a review of when I did this IUT book. That's what I call it. I said, okay, what are the falsifications? And so I covered that only a little bit because there have been dozens, maybe 100 books opposing the Big Bang. And I'll just point out some of the main reasons the Big Bang is false. And here's the first one. The Big Bang predicts that we should observe only young cosmological objects at great distances. Instead, we see elderly galaxies and galaxy clusters at the limit of observation. Now, that's about 13.8 billion light years, and that's what the Hubble has done. And of course, our prediction in infinite universe theory is that when the Webb telescope gets going, we're going to see even more of these elderly galaxies. And these galaxies that we're seeing that far away are already 13 billion light years old. So for the light to come here in a three-dimensional universe would be another 13 billion. So the universe is at least 26 billion years old. So the second one is cosmological objects often collide. Now, in actual explosions, objects are scattered in all directions, but they don't collide. The opinion that the third one is the opinion that the universe is expanding is dependent on the untired light theory. And that explains in detail later. But in untired light theory is Einstein's idea that it assumes that light can travel great distances without losing energy, a perpetual motion machine, which would have been totally thrown aside by Einstein when he was in the patent office in Bern, Switzerland. Nothing we know can travel from one place to another without energy, whether it's motion or the matter itself. Another one is the explosion in the universe out of nothing is a contradiction of the first law of thermodynamics, and otherwise known as the conservation of energy. And when Steve Hawking was giving his talk at Berkeley in, I think it was, 27, was it 17? 07. He talked on and on and on. And the best thing he said was Alan's little saying that infinity is a really long time, especially near the end. And I thought that was but what I wanted to do is ask him about this contradiction between the first law. Now, the first law says you can neither create matter nor destroy matter in the motion of matter. And they call it the first law of thermodynamics is the conservation of energy. And the next one is the Doppler effect, considered responsible for the cosmological redshift and the interpretation that most galaxies are receding from us, only occurs in a medium. Einstein's corpuscular theory of light denies the necessary presence of a medium. So a medium is why you get waves and why you have the Doppler shift, which many of you already know about, and we can discuss if you wish. Now, next one is Einstein's objectification of time is invalid. Time is not an object. Time is motion. The space-time concept, as used in general relativity and Big Bang theory, assumes time to be a dimension, which it is not. The universe is three-dimensional, just like everything we observe. Time, dilation, and other Einsteinian fantasies are products of ether denial. And you have to remember that. And we want to get into that. We will probably a little bit later. Why there's an ether, why it's already been proven to exist, and why it's necessary. Okay, the next one is the Big Bang theory is based on the assumption of finity. The most plausible assumption is infinity. There are over 2 trillion galaxies, like I said, and in the observable universe with no end in sight, an infinite universe cannot expand because it's already full. There's no empty space. Why would it expand? Okay, the last one is the existence of the universe implies that non-existence, perfectly empty space, is impossible. There is no definitive evidence for perfectly empty space. Infinity implies the existence of ether, infinitely subdividable particles. That's the idea. That's it as far as the complaints against the Big Bang, and the rest is just the development of its alternative, And the only one that can possibly be, and of course, there are all kinds of theories that want to replace the Big Bang, normally with reforms. They want to say, we're going to accept parts of Einstein, we're going to accept that because it's well proven and so on. And so you're going to have a mixture. And I don't think anyone else is talking about infinite universe theory in the way I am. And there are some, of course, infinite universe has been around for millennia. People thought, well, maybe there was no end. But what is the development? What does it require? What does it do to our interpretations about the rest of science?
Yeah, no, absolutely. But you say that nobody, but there are some. My father and I, like I said, we work in our model, even though it's not an ether model, it subscribes to everything you talk about. It's just different on that
Yeah, you just
sense.
have to put in some ether, then you'll be good shape.
No, we don't need it. We'll
You
talk
do
about
need
that.
it. You do need
No,
it. I'm going to
no,
explain
wait,
that.
wait. No, but let me say this. No, this we'll get to this and we'll talk about this near the end because I want you to explain your
Sure.
ideas about that. Here's what I think you really should be saying. It's not that it proves ether. It proves there's got to be light has to be a physical interpretation of something physical. Now, if there are more than one, if there's another model out there that does all the things that you're talking about, and is a based in neomechanics, it's based on infinity. That's what we have, and we talk about tired light. We talk about all of those things because the thing is what you are comparing is ether versus the photon. You're not comparing. What my father came up was, photon doesn't exist. We don't have a photon.
Well,
So
that's good.
what I'm saying is what I see, and we'll talk about that near the end because right now I'm gonna get into ether. I got some slides for you to talk about it because it's interesting. I think the change that I would make when I talk to people, I said, look, yes, Borchert's what he's saying is that you can't just say light is this thing that travels forever. There's got to be physicality to all of this stuff. And that's what we claim. And yes, we can do it. So in our world, it's that your claim it can only be ether, but our claim is it can be actually three types. We think there can be there are lattice types for light. There are also people that have particle model like ours, which is not a photonic model, and then of course ether. But let's put that aside. Let's not worry about that. I'm not going to argue that for now. But what we want to do is let's talk about your book Infinity, and you talk about ether, and you got some really interesting things, including calculations, and I've got some of those slides here. So let's start with that because the majority, I think almost everybody except for my father and myself, well, that's not true. There's some lattice people too, are etherists. So let's look at that here, and we'll talk about ether. And again, we spell it EATHER to make sure we're not talking about the gaseous ether, right?
Right, right.
And I've been trying to, I know that you have been pushing that, and I've been taking your lead in that. And I said, look, if you're going to talk about ether, don't spell it with an E because, then people think you're talking about what you get at the dentist office or something like that, right?
Right. Well, there's two
So,
kinds of ether, and I'm glad you used the A here because that has precedence. You can go back to Descartes
right,
and talk about that.
right,
And what was tested in Michelson-Morley experiment in '87 was ether,
right, right,
ETHER,
right, right,
and it has a different. The assumptions they were using were totally
right.
different from
Yeah,
what ether. This ether with the A is entrained around the Earth. The ether that they thought they were testing, was out in space and it was fixed relative to the Earth.
right.
And so they didn't get very significant result because of that, because ether is entrained. And you may have that slide that I gave you. It shows that the measurement that Michelson and Morley were trying to do actually can be done at higher and higher altitudes because the entrainment tends to decrease with distance from the Earth.
Right. Yeah. And I think that's the thing. The thing that their model was basically that ether was just sort of this gaseous kind of thing, really, that was sort of in the universe, and the Earth was moving through it, and it was somehow stationary, and they were going to find the movement within that, right?
Right. That's right.
And that's very different from what I call modern etherist theories. So yeah, let's keep moving forward here. This is another slide from you. So tell us about this.
Okay, this is Neomechanics, very cartoonish, but tells you quite a bit. See here,
Yes.
this is what the E equals MC square equation is all about. And what we're talking about here is, see this microcosm with submicrocosm inside and what we call supermicrocosms outside. And so what we have is on the left side, we have things that are these particles, the supermicrocosms colliding with this microcosm. And what are they doing? They're accelerating the ingredients inside this particle. The ingredients are submicrocosm, whatever they may be. They're subparticles of atoms or whatever. And
Right.
then on the right side, you see the reverse, where the motion within this microcosm is transmitted to the outside. You see on the right-hand side there,
Right. Right.
it says supermicrocosm. You have to have an outside. You cannot have empty space to do this. There has to be a supermicrocosm. That's where unienvironmental determinism comes in, the inside-outside kind of thing, and infinity as well. So that if you're going to have this equation E equals mc squared, you have to have ingredients. Now, a finite particle has solid matter. You see how the center of this microcosm, this portion of the universe, was solid matter. This couldn't happen. This negates the whole idea of a finite particle, and it also negates the possibility of a massless particle. A massless particle would have nothing inside of it. It's like Einstein's silly photon. It is a particle that has no mass, therefore has no ingredients, traveling through empty space, which also has no ingredients, which is telling you something, that it's totally imaginary. There's no such thing as a photon.
Sure.
Now, what is mistaken? Remember, let me mention this. What is mistaken for photon is essentially ether particles, and they're present everywhere, and they're colliding with things everywhere. And so when you get an analysis that says, oh, a photon hit something, like in Einstein's experiment, or his analysis anyway, photoelectric effect, what was happening? This was a particle that was hitting producing the photoelectric effect. What was that particle? The particle was ether particles that had already been around there and was now impacted by a light wave, which was motion in the ether, pushing these particles towards the anode that he was looking at. So anyway, this is again, I said this is what explains the E equals mc squared thing, and I have a paper on. You can read the details.
Okay, when you're talking about the E equals mc squared, one of the things in my documentary Einstein Wrong, I tell people I can make them doubt that equation in 3 words, right? And I mean, for the average person sort of gets it, right? That all mass is energy. So if you hold up an apple,
that's the misnomer again. It was a misinterpretation.
I understand.
Well, you see the equation here is E equals mc squared. Now, you can't, if there's no mass, like with a photon, m is 0. So what's E? 0 times something, whatever it is, c squared or whatever, is 0. So what is energy? What is energy? Now, the average person thinks energy is a thing, something.
Yeah, sure.
But it isn't. Energy is in a calculation of the motion of things. That's what it is.
No, so sure. And if you don't have to watch my movie, I'll give it away. The answer to my question, how to doubt it in 3 words, is what is energy? I mean, that's what, you ask a person, okay, E equals mc squared. Yeah, it's like everything's energy. And I go, okay, you want to make me, I'll make you doubt it. And they go, no way. And I go, what's energy? And then they start to, then all of a sudden they realize that you can't describe, because they're looking for a thing, right? And they're not going to find it. So
yeah, remember they say that energy is converted into mass. Now, look at this. Look at what we're showing here in this slide. what we're talking about is the submicrocosms and their velocities. And when you impact them from outside, the velocities increase, okay?
Hmm.
And when they increase, they do something that is measured as mass. What is mass? Mass is the resistance to
Right.
motion,
Right.
okay? So when you have this on the left side, you have this impact, and you increase the velocity of the submicrocosm, what's going to happen? You're going to have a greater resistance to acceleration. You know,
Right.
if the ingredients inside something are going faster and faster, then you're going to have more resistance. And likewise, on the right side, if these things impact the outside, they're going to lose some of that motion. That motion is transferred to the outside. And
Right.
so what's going to happen to mass? The resistance to acceleration is going to decrease.
Right. And I think the way I sort of describe to people, I said, look, energy, the way we describe it, is some useful work we get out of motion, right? We can
Right.
we can hold in our gas tank, atomic structures and molecules, and those things have movement inside, and we know how to release that in a way to actually in the outside in the super microcosm, uh, to get motion and get our car moving. So it's really it's a concept, right? It means, and the energy really, in the end, is what, when we are worried about, is more useful. But yeah,
Yeah.
I love these diagrams because you really have to stop, take a look at it, and think about it. People don't. I mean, if you don't do that, you're not going to get the idea. And this, of course, who drew these in the first place?
I did.
Oh, you did.
Yeah.
Okay. Okay. So
Yeah. I
yeah, I
remember
mean,
not some are circles because it was easier to do, but remember the microcosm here, cutaway view of microcosm. See how
yeah,
irregular it is? Sometimes it has
yeah,
holes. That's
yeah.
what reality is. It's
Oh yeah.
not round. It's not spherical like Democritus thought and the other finite particle folks. Maybe they'll have
Right.
a different configuration, but you can't have configurations unless you have submicrocosms to make up that irregularity.
Yeah. No, absolutely. No,
Okay, but
that's
the other thing I was going to mention here is that E equals mc squared is what I call a matter dash motion equation. It's like
right.
momentum. Momentum is P equals mv, all right? And there's no such thing as momentum.
Right. Right. Right.
Things are XYZ portions of the universe. And so it's also an equation, and it explains what is happening to matter in motion.
Hmm.
And so when you get hit by, for example, a linebacker going at high speed, he is exhibiting a lot of momentum, right? And so but that's the M. If it's a big one, you're going to get hit harder than if it's a small one, if he's going faster and so on. That's what the MV part is all about. But it's just a description of matter in motion. That's what E equals mc squared is. Same thing. Energy is a description. Force is likewise F equals ma, mass times acceleration. That essentially tells what an effect is. In order to have an effect, you have to have something colliding with something else.
Right.
Remember, an
Right.
infinite universe has that. Neomechanics talks about that in an infinite way. Here we only show a few super microcosms, and there's an infinite number of them.
Yeah. Oh, I'm going to put this up. It's very interesting. This is a common argument that obviously people make. For instance, like the relativistic kinematic equations. When I did my movie Einstein Wrong, one of the things is that the reason you have these particles like neutrinos and other things is because when you get this idea of relativity, and that somehow motion causes a change in the actual matter, like it gets bigger, or there's more energy, or there's more momentum somehow, right? That's what it's magical. That these equations when you start criticizing an equation like this, E equals mc squared, they're going to immediately throw on top of it. What I look at it is they take something that's already problematic in philosophically, right? Just
Right.
philosophically. And then on top of that, they throw in magic, really. I mean, that's what relativity really ends up being. In fact, it was interesting in my movie, Einstein Wrong, is that I have a guy who stands on the hill overlooking the Stanford Linear Accelerator in my movie because they didn't allow us in. They called me up 5 days before we were supposed to film inside for the film and said it was in the best interest of our community that you don't film your any scenes of Einstein Wrong in the Stanford Linear Accelerator. Well, this guy was one of the few people. He said people told him not to do the film, but he literally stood there and said, "We have to unteach relativity to our experimentalists, our students." And so what you have here is a person, I mean, first of all, they rely on math, right? And the moment you rely on math, they forget the number one thing, and that is two things. One, math is flawed. I mean, we have negative numbers. There's no negatives in the universe. We just picked an arbitrary point, and then when we were at the word one, we put a minus sign in front of it. So
Right.
we're already using a flawed system. And then on top of that, we are using all these equations that are useful to do calculations to manipulate the world. But people then take those things to become they are the world.
Yeah,
When
right.
I gave our book on our particle model to one of my colleagues, he couldn't get past. He put it back on my desk as if I had given him a toxic book, right? And he goes, I can't even get past the idea that gravity's a push. Gravity's a push. And then I started, so what do you think it is? He says, well, it's space time and it's tensor equations. I says, well, tensor equations. I said, look, first of all, I've got a bachelor's in mathematics. I love math. Math is a lot of fun. It's a wonderful system. I enjoy the system of math, even though now I know it's flawed in a lot of ways. But I said, well, it's math. It's a way for us to describe what's
Exactly.
going on.
Right.
And he, you know what he said back to me right to my face? He goes, no, tensor equations are real. They're physical things.
Huh, yeah, right.
And
I think I got a good example. The problem with math is wonderful, and I've used it, like you, so much. And one example I think is good. Time is motion, and so I get a lot of people who say, "Oh no, time is measurement of motion." Measurement of motion. Okay. So now you have to know the difference between reality and the measurement of reality. That's what a lot of this all comes down to with Einstein's. I remember you have different observers that get different results in Einstein's
yeah,
relativity. Well,
yeah,
really, the result that you get, and you can use some of the interpretations that they come up with. And if you use the medium itself as the reference point, you get accurate measurements. If you don't, you'll get things like time dilation, all kinds of nonsense like that. And time, of course, is motion. It can't be dilated. Only things can be dilated. And so this is the kind of thing that happens. You need to know the difference between measurement, math, and reality. And
right, right.
people who work with reality, like maybe you don't as much, but I work with reality and earth science. That's what we do. We have our feet on the ground. We use math all the time, but I think, have a better feeling for it than people
Well,
who sit in the office and only do math.
right. No, and I'm not one of those people, even though I sit around just manipulating symbols all day. That's my job. But I have found that engineers, and especially electrical engineers like my father, they seem to be one of the best groups at critical thinking, feet on the ground, because in the end they're having to deal with real stuff and
Yeah.
making it still. But they seem that this engineering attitude is something I've seen over the last 3 decades, being involved with what I consider to be very good critical thinkers.
Yeah.
It's you can talk about, you understand the way I look at it. I don't know if it's my father who said this or I can't remember anymore sometimes, but it's like, the mathematics we have, we just try to cobble together some kind of system to crudely explain the way the world works. It doesn't tell us the way what is really happening in the universe. And I think that's what people get mixed up all the time, right? They just are constantly saying to themselves that, oh, they get so involved with the math, the equations become in this one symbol, and they deal with it that they're starting to forget. The average person on the street's looking at all this manipulation, these equations that are, absolutely ungodly to try to understand. And then they go, what's light? Can't answer
Right,
it,
right.
you
And they
know.
still don't know what light is.
Yeah, they don't know. And it's funny because I see all
Particles.
these,
Yeah, yeah,
yeah, I
right.
see all these things on the internet and Facebook and people making comments and they're, the equations and stuff. And they say, well, Dave, what do you think about this? And they describe what's in, the articles describing all this stuff going on. I go, all these things they talk about, like gravitational waves. I said, this is really interesting because they have no physical model for gravity. How are they finding waves in it? I mean, if you really think about it,
Yeah,
that's the real problem. The real problem is there's no model for light, there's no model for gravity, there's no model for magnetism, none of those things. And ether models will try to answer that. Other models try to answer that, and I think that's where we are today. We're in model revolution,
yeah.
and we're fighting it out. I mean, there's the etherists, there's us, there's some other types of models, but the idea is all of us, and well, many of us are using infinity, and all of us are trying to give physicality. That I think people are just tired of it. We want to know what it is, right? We know what it is. So let's go forward with ether. I've got another slide up here. I've always thought this interesting, and you've been talking about this lately. And I know why you have because I've talked with you. But explain to me in your model of ether for the universe, why does the you think that the ether perhaps would look like a vortex or disk?
Okay. The vortex is so common in the universe. In our book with Steve Pitts, we talked about that a lot too. And this Umbrella galaxy kind of gives you an example of what an ether particle might be like. A lot of people have drawn them as spheres,
Right.
and I don't think so. I think because the vortex model is so common that we should think about ethers being a vortex like this. And there's some evidence for that. One of them is that light waves are T waves.
Hmm.
They're transverse. The motion goes essentially side to side, not this way back and forth. And that is typical, I think, of this kind of particle. So imagine you had a whole bunch of free frisbees in the room and you wanted to move them along. Guess what would happen? Most of them would squirt out the side
Right.
transversely. And that's what we're seeing in light. So this is why I think this is a possible particle that ether might be. And remember, it's capital A here, like you did correctly. And not that it's, whatever kind of ether Michelson Morley thought they were doing. It's not that. It's this. Now, a lot of people have said, okay, there's a solid ether of some kind. Because remember, solids have T waves.
Right. Right.
And of course gases don't necessarily. So but in the case of ether, it's definitely T waves motion, and so you're going to have some kind of reason for that, and this is one reason.
Right.
There may be
Right,
others,
right.
and
So this is a solution to one of the criticisms of ether, right? One of the criticisms of
yeah,
the ether that it couldn't do transverse waves, and what
yeah,
and obviously if you can't explain that, if people see that, then they're going to want an answer to that. So I thought that was a
yeah,
very interesting. Yet I don't see. It's really funny. One of the things I criticize about etherists, and I'm not saying that they're wrong because I'm even though my father and I have a working model that does just as well, it's not a photonic model. It's still up in the air. This is why we're in model revolution. Is it going to be ether? It's going to be a particle model, which is white. Light is really just waves of particles.
there you go. That's
That's
what ether is. That's
well,
what
no, no,
light
no,
is.
no, 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 no. That's different because our
I
our
know.
part our particles are different. They're not bashing
Well,
against ether.
remember the difference between etherists and particleists. First of all, particleists like Einstein says that the particle of light, the photon, left the galaxy 13.8 billion light years years ago, and it then hits your eyeball. Okay, and if Einstein was doing sound, he would call them the sound is produced by phonon by by soundons.
Something like
And
that. Yeah,
the,
yeah.
yeah,
Phonons.
right. Instead of the waves in the particles, and ether's waves in the particle. So the motion that is produced by the galaxy is transverse, and it moves through the ether and as waves. And the particle that left, if there was a particle that was involved, of course it doesn't hit your eye. That part, it's a wave within the ether, within the medium, just like sound is the same thing. There's no such thing as the nitrogen leaving my mouth and hitting your ear. It's the wave in the nitrogen, and that's why you need to have a medium, and that's why light is a wave and not a particle.
Yeah, I mean, I understand that explanation perfectly, but like I said, there's again, we don't have a photon model. What the difference is that in our model, light are traveling groups of particles. So when you
Yeah,
get
well, you can
what,
do that, but that's still a particle theory because you have a microcosm of a group that's moving,
yes,
and that's not what's happening.
well, no, we're not going to argue that right now. Okay, let's not
Okay,
argue.
let's
It's
let
not. It
that.
really is. It's not really worth it. That's
Yeah.
okay.
Well, you'll convert eventually to ether, so don't worry.
No, no, that's okay. That's
We'll
okay.
see you on the other side, David.
No, 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 they won't. Okay, that's okay. That's not a big deal. And that's what's most important is we're
But it's a
here.
really big deal, though.
I do understand it. And
Without ether, this infinite universe theory doesn't work. Without it, doesn't work.
no, that's, well, you can say that, but we will
Well,
dispute that because we use the
study
infinite
the book, study the
universe
book,
theory. And
read
we have all, we can
the
explain.
book, read the book, and then you'll find out.
I did. I read the whole thing.
I'll give you.
Here's what I'm saying. Here's what I'm saying. Okay. I mean,
Remember anything in it?
I told you this is going to get contentious, but let me just say this. Let me say this. I guess the only problem I have, and this is the same way with the etherists, they're not checking out what we're saying. What you're doing is you're assuming certain things about what we're saying, and it's not true. And so what needs to be done by etherists, just like I do, when any new theory comes out, when I read about your theories, I read about the ether, I read about all these things. I read about tensor equations that a guy here says I don't know about, and therefore, I look at those. The problem is people, I know your conclusions, I know where they're coming from, but you have never sat down to say, okay, what are they saying? And in some sense, the way that people treat what an alternative to ether is much like what the mainstream does when they treat your theory. They're going to, instead of looking at what you're saying, they're going to immediately go to a page where you say something and immediately say that's stupid. Just like the guy we have in the chat, whose basically only argument is, of course, you don't understand tensor equations, David, which is not true. I'm a mathematician, and therefore what they do is they pick on the one thing. So the only thing I can say to everybody who says ether is the only way is that they haven't taken the time to look at what we're saying and to fully. And that's okay. I mean, we don't expect, because our book's not out yet. So that's all I'm saying. So number one, I'm not here to argue that. What I want to know is to understand in your theory, which I say these two theories are in my opinion the most viable right now, and one of them will win out. And if you're right, then I will take my hat off you. But if we're right, then that's
Sounds
okay.
good.
But
It's a beer on that one.
yeah, exactly. So what I thought was super interesting here is that you, again, I'll repeat it, unlike other people, are trying to solve these problems. It's really interesting because somebody was mentioning Domina Spencer. Let me see. Here, here's Richard Jess, who knows Domina, right? Who I guess he's a older member of the MPA, and he said Domina Spencer wrote a book on Hollers, which is the general case of tensors. I didn't understand a word, but they were there, et cetera, et cetera. But one of the things I'm mentioning her is she was always, I don't know if you remember, she
Sure.
was always, anybody type said ether, she'd be sitting up in the front of the room, and she would, person would be talking, and then all of a sudden she goes, ether does not exist. We do
Yeah.
not
Yeah. And she
need it.
was so neat. And being 90 years old or something, she was a positivist. A positivist loves empty space. There's nothing in it. And the idea is that if I can't see, touch, smell, whatever, then it doesn't exist.
Right,
And
right.
one time that was pretty good because that got rid of a lot of magical thinking about ghosts and things like that.
Right.
So she used that, and she didn't even know she was a positivist. I don't think
Yeah,
she
yeah.
didn't understand philosophy very well. And so, but she was quite a character,
Oh
and I
yeah.
always say, "Oh, if there's ether, bring some into my lab, and I'll test it."
Yeah.
And if you're going to show the properties of ether, it's the particles are so tiny,
Yeah, I know. We're going to talk about
and
that. We're going to have that come up.
we should talk
Right,
about
right.
this. Get enough time
Right.
for that.
We'll talk about that. And that's what I think is fascinating too. What again, going to that point about the ether, and we're showing the that you think it's like a vortex. I mean, I think what that is doing. One of the things that's doing is addressing the problems. When if you go back, the people who are younger today weren't around with the MPA, and one of the things the MPA did do well for the ether theory was to challenge it where it was weak, right? I mean, it really was weak from the older ether theories.
Oh,
For instance, yeah, I mean, there was
yeah,
no entraining. There was no entraining to ether.
yeah.
There was no how do you do transverse waves? And the problem with the etherists, they just and I will say here's the other thing, Glenn. And this is where I'm on your side. The etherists of today don't even care or think that transverse waves even matter. All they do is they're so fixated on the idea that light has to be in a medium, and then they want to figure out how gravity works, and they're in that world. And I said, okay, is it ether round particle? How do you do transverse waves? And they look at me like, who cares? It doesn't matter. And yet, a
Well,
person
it's
like yourself,
fundamental. Yeah,
it's
yeah.
well, absolutely, it's fundamental. But
Equator-
so the etherists today, Glenn, are just completely ignoring the major problems with it, and you aren't. And you are trying to answer those. I mean, the gravitation, and I think in of all the ether theories, in my opinion, yours is obviously, well, obviously, in my opinion, the most advanced, and you are treating that. So I think that's really fantastic. So let's go to the next slide here, which is the actual calculations. I was fascinated when you started talking about this. So I want you talk about this here, the summary of speculative calculations on the property of ether particles and the ether medium. So I like the word that you're putting speculative instead of these journalistic things like well founded, and put in 1,000 university names in that place of the calculations, and then list the people who have Nobel prizes who agree with what they're about to present. I don't know. You seem to actually follow the real rule of science and say these are speculative, but I still find them extremely fascinating. And I want to know, and I think other people want to know, how did you come up with these? Explain first what they are, and then how you came up with them.
I don't give the derivation here. Again, it's so speculative. It's from Planck's constant. Now, remember, Planck's constant essentially hypothesized the smallest interaction that could be measured by anyone, and Planck's constant is pretty well accepted. And so what I did is I said, okay, ether particles crashing into something are what is causing the Planck's constant's veracity, you might call it.
Mm-hmm.
And from that, then I calculate these various constants. So a mass of 10 to the minus 47 grams, a diameter of 3 times 10 to the minus 19, and and the volume, subsequently 10 to the minus 57 cubic centimeter, and then a density of 10 to the 10 grams per centimeter cube. Now, just think about that. Quartz, which we're all familiar with, rocks, 2.65 grams per cubic centimeter. Here we have 10 to the 10th. Nothing that we know of, I think, has that kind of density. So that's one of the things about. Now, that doesn't mean
How
that
about a
it's
black hole?
that is very, very dense. Okay, and again, of course, the rest of it, the particle velocity goes from near zero to 4.5 times 10 to the 8. Now, you remember that light is just essentially 10 to the 8 meters, or 3 times 10 to the 8. So this is an analogy from sound. Now,
Right.
the particles within the atmosphere, the sound travels at 343 meters per second, but the particle motion, interparticle motion, is 50% greater. It's essentially around 515 meters per second.
Right.
And that's the analogy that I'm using here to get the particle velocity. And just to tell you that, okay, so light does have a more or less constant velocity, like the velocity in the atmosphere is for sound.
Sure.
But it does vary. Everything in the universe
Of course,
varies.
of course.
There's
There are no constants,
okay,
are what you saying?
no constants. There are only approximations. Remember, in infinite universe theory, every measurement we make has a plus or minus,
Right.
except for a few mathematicians that don't quite ever do an experiment. But if you ever do an experiment, you'll find out you don't get the same result twice.
Right.
You get a different result
Sure.
if you're precise enough. Okay. So now look at down here where it says number in an electron,
Right. It's absurd. Right.
10 to the 20th. Just think about that. This is how you get these, you know what electron's mass is. It's 486th of a hydrogen atom. So that's how you do it. And now the composition is ether 2 particles, and we explained this whole system in the universal cycle theory.
Yeah.
Yeah, yeah. And if you're really interested, but ether, this is what ether is made. Everything has to be made of something, right? That's what infinite universe theory is about. So ether 1 particles, if you will, have to be consisting of something. Remember when you saw that sombrero galaxy, you see particles in there, and that's very good because that tells you that ether itself is made up of other ether particles that are smaller.
What's the electron made of?
Ether particles.
Okay.
Ether 1, yeah.
Okay. All right. And then you have the ether medium velocity variable, okay, and primary type of wave, a T wave. Okay.
Yeah.
So this is a question I think you've answered, but I just want to make sure. I want to, people are typing them. It says, question to Dr. Borchardt: Is the light speed constant? If constant, then relative to what? I think you've sort of answered it.
Oh, it's the same. It's the same as with the sound traveling through the atmosphere is constant at 343 meters per second, but it varies by altitude and other conditions. And I think ether is the same thing. Ether is a real thing. It's like everything else.
Right.
It's affected by macrocosm. So it's relatively constant. And when we explain, for example, the Pound-Rebka experiment, we explain that the ether does change with distance from the Earth. Instead of dilating light, what you have is more dense ether near the Earth, lower pressure, greater pressure away. That's why you get gravitation.
Right. Well,
but it's different. It's not the same. It's within 10 to the minus 15th, but it's different. That's why you get what they call gravitation.
Well, guess what? Here we go. And that is gravity, because one of the big things in our conferences constantly are people who are etherists, which is the majority of them, and they are always working on gravity. So let's take a look at what you have here. So I got these from your slides. So let's go forward and talk about gravity. We're at 11:22. I mean, I thought we were like, time is I hope other people are enjoying this, because I certainly love this stuff. So talk about what you see now. Gravity. How does the infinite universe theory talk about gravity and ether in this case?
Okay. Remember the Lesage theory that was popular, and it still is popular. It said that particles came from elsewhere and would go through the Earth or hit the Earth and go through. And I don't see it that way. I see it as simply a pressure effect.
Right.
It's like, say you have a balloon, and how does that balloon get bigger or smaller? Well, it depends on the environment in which it is. And here you have these gravity ether particles are zipping around at upwards of 1.5 C, and they hit baryonic matter. They hit the Earth. This is why this ether is entrained. Anytime you have an object that hits another object, what happens to it? What happens to that billiard ball, that shooter that you're using? It slows down after it hits something.
Right.
So I demanded in my paper on this, I submitted to 3 different places, very well respected. And the best I got was, well, we already know what gravity is, and it isn't this, right? So it's not physical, space-time, and so on. and other magical stuff, and then at the same time it's an attraction, which we have no mechanism
Sure,
for. It doesn't make any
of
sense.
course.
So here you have baryonic matter being hit by ether, and what's going to happen? It's got to slow down.
Right.
And when it slows down, it accumulates around baryon. So everything in the universe is going to have ether surrounding it. Now they're thinking, oh, this is dark matter. They can't get the calculations to work for the rotation of galaxies. And so now they're talking about this as, I think ether and dark matter are one and the same. People who don't like ether don't like dark matter. The cosmologists obviously have to use something to explain their situation with rotation of galaxies. And
well, actually, that's one argument I would say for you. If I were you, I'd just remove that argument completely. The reason is, well, wait. Here's the problem. No. Because you can use Newtonian gravity or even your gravity to explain the velocity, and it has nothing to do with mass that isn't being seen. It's a completely gravitational problem, meaning it's not gravity from particles we don't see. It's not dark matter. Dark matter doesn't exist. We have one person who calculated using Newtonian gravity, because the calculation for Newtonian gravity more or less work. It's not that we give the mechanism for it, right? It's not a mechanism, but it works. So
Vera Rubin's great work. She has a nice.
The problem is that you are saying there's an anomaly, and that anomaly doesn't exist in the Newtonian world. So that's the difference. So that the problem is we treat these disks with a gravitational field as if they were spheres. And so when we go to calculate the edge stars, we think they're anomalous and that Newton can't explain it and there must be something else there. There isn't. We can explain it. Newton explains it, because the gravitational field at the edge of a galaxy is much higher than above it. It's not a sphere. We know that the gravity field between the Earth and the Moon is not a spherical one. If it was, we would shoot things straight toward the Moon, and it wouldn't. We can't do that. So what I'm saying to you is, it's not a necessary for your theory, for gravity with ether, for everything that I see. It's not necessary, because dark matter doesn't exist and can be explained by gravity. You don't have to say that the ether is the gravity. What it is your gravitational field, and Newton's gravitational field completely explains what we think are anomalous velocities on the edge of the universe. That's all I'm saying. What I'm saying is, if dark matter doesn't exist. We know that the calculations work with Newton. It's just that no one applies gravity in that the complex gravitational field around the galaxy. And therefore, if you do that, gravity explains it. So you don't have to explain that there is dark matter. There is no dark matter. It's just that gravity explains it. Your gravity with your ether model explains those. If we were to take a model of your gravity of ether with entrained ether and saying that's gravity because it accumulates, which in your model works totally fine. Those stars on the edge of the galaxies aren't moving different. They're moving completely in line with what you're talking about. It's not missing matter of ether or anything. It's just gravitation. Because it's also very funny that the two galaxies, and this is where I think there's proof that there's no dark matter, the two galaxies that they found without dark matter, and they say it, are spherical. They're completely spherical. So what does that mean? That the edge stars are going to be completely predictable by a point mass. You know how they use point masses. They love point masses. Sure. And the truth is that that's not what a galaxy is. A galaxy is not a point mass gravitation field. If you send something in through the middle of a galaxy through its main core, it's a very different gravitational field than if you just if you nick it or something like that. So what I'm saying to you is that the argument that you use about dark matter is in ether's dark matter. No, your gravitational explanation will work
through this figure here. When ether particles hit baryonic matter,
right,
they are decelerated. Okay?
Right, understood. Yeah.
So this is
no, this works really great. I think the entrained ether for gravity works quite well. That's a good model.
And so there is a reduction in the pressure that is near baryonic matter, because that's what this is all about. So if you went away from this baryonic matter, the pressure would be greater. The
Right.
pressure is lower by the baryonic matter. Guess where these particles are going to be having their greatest effect? They're going to go from high pressure to low pressure. This
Right.
every weather man knows about that. Weather person knows about
It's
that.
the it's the shadowing effect, right? I mean, it's just, it's very, it's
Not necessarily that, but in a way, there's
the
some
pressure.
shadowing of
Yeah, it's the
pressure
pressure. Yeah. Yeah, absolutely. No, I understand that. It
pressure
works.
difference. You have to slow down these ether particles, and when you do, they accumulate around the baryonic matter.
Right.
And I don't know if you got that
Lem-
figure for about Newton's idea of push
Right
theory.
there.
Yeah, there you go. Let me explain a little bit about it. I'm not expect anybody to read this old English, but essentially what he said is that the universal medium had increasing distal density. Okay, distal means away,
Right.
proximal means
Right.
close. Okay,
Right.
and so he just got it backwards, because the density in see, because it has no explanation
Right,
for
of course.
why that.
But the good thing about Newton, he said he didn't know, right?
Yeah,
That's
well,
why I
that
always
is,
respect Newton, because he always told everybody, look, I can maybe describe what a gravitational, how bodies work in a gravitational field, but don't accuse me. I don't know if he said that, but don't
well,
accuse me of knowing how it works.
but he's making the attempt. He's thinking about that
Right,
here.
right, right,
The fact that he got it backwards is that's why it didn't fly.
right, right.
And attraction, of course, is very much for self-centered people. Attraction is where it's at, right?
Yeah.
So and
I
so
never thought about
people have
that. Wait a minute.
yeah people
I
have
thought this was full. I thought you were a philosopher, not a psychologist. So.
no philosophy and psychology. Is there a difference? No, I didn't think so. Yeah. So anyway, that's what he was doing, and so he just got it. Medium goes towards the rare. He wanted to say the medium was. So you have two things with a medium: pressure, which is the activity of the particles, and the other one is the density.
Right.
And if you're going to make something, the density has to increase. You're bringing things together. What does that
Right.
do? That's increasing. So matter itself is the bringing together of these ether particles, and they're forming ether complexes. That's all we have. That's what things are made out
Right.
of.
I understood. I understood. Here's a good question I want to just put up here because there's some good chatter going on here. How does the 0.5c get back to up to 1.5c? I think I know the answer, but
Well, it doesn't, and it can be hit by other particles,
well, it can be
right?
eventually. It can be accelerated again, right? I
It can
mean,
be accelerated.
yeah,
But what has to accelerate it? Other
other ether
ether particles.
particles. Yeah.
Yeah, which are in turn going to lose some of their motion. This is
So
why
wait a minute.
the
Wait a minute. Are we saying that in your theory, the whole motion will eventually go to the whole universe will stop then?
oh no,
I mean,
it's
if
only
you
around these
how do you have 1.5 C's and then 0.5 C's, and if you're saying that you can't get back there, then you have a directional thing, right?
yeah, it's just related to. So what we are talking about is parts of the universe in which the ether particles have slowed down. The production of anything is the slowing down of ether particles. That's all it is. And it's in one place slowed down. Now, that would mean that a thing once formed would never ever come apart, would be immortal, but that's not true, because the particles are still in motion and eventually leave that area. Everything in the universe, every microcosm, every galaxy
Right,
eventually meets its death by what? Divergence.
right, right,
According to complementarity, there's got to be divergence for everything that comes together, like you and I. There's a coming apart, like what will happen to us. Well, like, for example, my hair disappearing and dispersing throughout the universe. And so that's what's happening to every single
right,
thing. And
right.
so, yeah. So do these parts get up to 1.5C again? Yeah, maybe some part of that. Yeah, sure. Why
Yeah,
not?
yeah, that's what I would say too. Yeah. I mean, here's another thing that drives me crazy, and again, it has to do with, I know neutrinos always tick me off, but the problem is people don't go and look at the history of anything. And one of the things I know very much is that you historically, not only with science, but also with philosophy, one of the things that always impressed me, and it's something that I think all of, well, people I think who are true critical thinkers do, and that is to look at the history. I mean, the problem with people is they'll take something and say, "Oh, neutrinos, they exist." They don't go back anything I say, anything. If I even the electron, when we were looking at our model and we had our idea what the electron was, well, I went back and I said, what do we really know about it? Because people can tell me it exists all day long, but I'm going to go back and myself look at it, right? So what we have is you're looking at ether. You've been talking about ether and the neutrino. Has a person gone back to look at where the neutrino came from? Why was it even postulated? And one of the things I've seen in the dissonant world is they throw out the history of it. They don't care where it comes from. Yeah, in Dr. Karazani, my mentor, who got me into this, who pointed me in directions to find people like you, Glenn. Well, he figured it out. What it was is that at the time when you were looking at decay, where obviously you had this mass there, and there was a microcosm where things were going out, right? It was releasing, right? I mean, it's releasing energy, what they call moving particles. Actually, so you'd have this mass sitting there with no provocation. Well, we know that's not true, but it's sitting there, and electrons are coming out at the speed of up to 0.86 this time speed of light. Well, everyone's, if you use relativity, the crazy idea that you can have more mass, well, they said, guess what? According to relativity, that's what Pauli said. If you guys are looking at relativity, this mass that is decaying and the electrons coming out, we're not measuring in our calorimeters enough energy to make up for that magical energy that special relativity had. So what did they do? He postulated a neutron, which of course was actually taken. So when Pauli died, Fermi took over that and said, "Oh, we'll call it a neutrino." So when people, if you don't go back in science and take a look at these words you're using, especially, I don't know, Mr. Arkeef or whatever, how do you say that name? That's down here. Please don't go and assume the things that what you read exists. I think what happens a lot of times, Glenn, is that what people want, and especially if they're dissidents, like you have an ether, I'm going to go to find it. Maybe the tendency to say ether is dark matter is our desperateness emotionally to try to find something out there that we can hang our hats on. That's
That's it. Okay. The reason that dark matter is invented is because the Newtonian equations did not work,
well,
and
they do work if you do apply them correctly, is what we're
you'd
saying.
have to you'd have to write a paper on
It's
that.
already there. It's already there. I can send you the link.
Okay. Now, in regard to neutrinos are such a tiny speck of matter. I don't know, what is the mass of a neutrino?
Oh, no, it was no. Look, the neutrino was invented because special relativity didn't. It said there was more stuff. They said no. At first they said they had no mass and no charge. And the if you look at the neutrino, if you have any type of logical mind, even I think under your infinite universe and neo-mechanical world, you're going to have to eliminate the neutrino because it's based on the observation and it's based on Einstein's relativistic kinematic equations. That's what it's based on.
Yeah,
so
right.
so if you yeah, I know, but what I'm saying is if you Glenn Borchardt say that relativistic kinematic equations are wrong, then you have to throw the neutrino out because that's where they come from. And the problem is if you talk to neutrino people, they're going to say, no, it's not true. And what they do, it's the same thing with anything that they try to defend. They try to defend its initial assumptions of where it was. It's like dark matter. If you say to a person, we have Cameron Ribisol has done the calculations using Newtonian mechanics and the Newtonian calculations to show that the stars on the edge of the galaxy. We have a paper. If you want to know it, go look up Cameron Ribisol and go to our Wikipedia. He has an entire paper with all the calculations where he breaks down masses into arms, just like a galaxy, and he makes the calculations for that. Then we say to people, no, it's not an anomaly. In fact, Newton can explain it. The same way with the neutrino. So what I'm saying to you is the neutrino is totally based upon the assumption of of the relativistic mechanical equations. So if we go back, what you're saying, I'm going to get back to, because we're running out of time. This is this great conversation here. That you're saying is with gravity, that Newton had an idea of the difference of the density, but he had it backwards, is what you're saying.
Right. Yeah.
Okay, so let's go to what else do I have? Okay. Oh, this is what I've been talking about. I think this may be. Oh, here we go. This is another thing. I know there's so much to talk about. Like you said, Glenn, we could be here for you and me. Could be for. I want to come out to Tahoe with my father, and we'll just sit there for days and talk
That
about
would be
stuff.
great.
We'll be fighting out
We might have to
between.
wait a few months.
Yeah, exactly, with COVID. But this is really an interesting part that you've talked about. And again, folks, I'm sorry, there's just so much to talk about with the ether. We're trying to get I'm trying to talk about all the things that Glenn touches upon, which he's had a few decades to think about. Tell me about this, because what we're talking about is something that when I first came across dissident science, when I first met Dr. Karazani, and he showed why the neutrino doesn't exist, what went wrong there. He showed the calculation problems that were wrong, the assumptions that were wrong with special relativity, which he turned in. He is a complete three-dimensional Newtonian world kind of idea. Newtonian, not in the infinite, not mechanics, but that thing. The first thing I did was to look at at science, because I'm saying this is a big change, right? What you're proposing, infinity, the infinite universe theory, even the ether part, these are big changes. And one of the things that we humans have, and what I did, I immediately went to the library in Long Beach, California, and took out every book I could on this history of science. When does it change? Why does it change? And I think that's what this graph is about. Is that correct?
Yeah, well, it shows the population. What's quite often not recognized by most folks is that in 1989 we reached the inflection point. What's an inflection point? Well, that's the point from when you get rapid exponential increase to a slowing of that increase.
Right.
So many curves in nature are like this. They're sigmoidal, S-shaped curves like this.
Right.
And so what we have then is at about 1989, we have about 5 billion people.
Right.
And the Big Bang is going rampant. If you see,
Of course, yeah.
over the 1900s, you have the Big Bang show up. Look at these, when you have more or less solid lines, that's the age of the Big Bang. It fits with our tremendous economic expansion, which I correlate 1-to-1 with population.
Right.
So what is going to happen? Look at what you're going to see as you approach the year 2050. There's going to be a big change.
Right.
In population. We're seeing it now. There's a general slowdown globally. These are global numbers. We're now at about 7.3.
Right.
What I did here to get this curve, I simply took the data up to 1989, and then I flipped it.
Right, exactly. Yeah, I see that. So you can see the same points there, right? You see these three as a group. There's a three, and you can see these group.
Yeah, exactly, and that's what I did. And remember the population folks from a Population Reference Bureau and the U.S. Census and so on. They have a high value for population expectations and a low value, and this is about in the middle. And I thought it was kind of neat because I had devised this back in 1989 and about actually in 84 because I could see some of this coming already. And they come up with this curve. And it's not all that different. And if you're going to have 10 billion people as our carrying capacity, which we say is the maximum that the resources will, now, a lot of resources have to do not only with what they are, how much food or land there is, but the energy that is required to work with those resources. So when it gets harder and harder, for example, to get water, to get gold out of things, what happens? You slow down. That's what we're going to see here. And so a big change will occur about before 2050, around that time. It's going to, because this is going to be huge
So,
change. We're
so,
going to
so
go,
are you saying, I understand, but are you saying there's going to be a big crisis, some type of social crisis? I mean,
right now.
we're already seeing the beginnings of that, right? I mean, we're seeing that people are realizing, wait a minute, why is it as a human being, if we are a advanced race, where you are born determines your quality of life, and that has to do with resources in the population, obviously. So what are you saying? Maybe I just want to push this along because we're at 15 minutes before the end here. You're saying that this graph to you is to say, okay, where would a paradigm shift be? Where would we give up the Big Bang? Where would we start to look at models such as ether? Is that what you're saying?
Yeah, right. And and so you can have a big philosophical change and all things that go with it. People are going to, you know, well, what we're seeing now is a breakdown in the economic system. Growth is slowing down along
Right.
with the population. And so we're going to have to make do with separate, we have to decide who gets what, right? Are we going to give all the money to the 1%? Are they going to, six people probably own half the country now. Are we going to
Sure.
give them the rest of it? What are we going to do?
Right.
And so you're seeing right now, the first thing that people do is they move to the right because the right says, let's go back to the good old days.
Right.
Let's go back to February 1955 when everything was perfect. And now that's what people are trying to do. They're thinking about, but eventually, once we find out that doesn't work,
Right.
that old stuff doesn't work. Those old ideas, the old Big Bang and so on, that and all the traditional beliefs that go with it, they don't work. And so we're going to have to devise something else. And that's why I say we have a lot of grief coming up in the next 30 years.
Yeah, that's
No
great. I
kidding.
know. I know. And it's
It's no longer individual countries. It'll happen in individual countries. One will change to fascism, the other one socialism. But that's that yin yang you're going to see. And what do we do in politics? We overdo things and we underdo things.
right.
We Nobody knows what exactly to do, right? So every one of us is an experiment. Should we teach our own kids or should we have someone else teach them?
Sure.
How you go back and forth on that.
So,
So it's very interesting. I wish I could be around that whole 30 years.
yeah, yeah. I think, and again, I did a video on this where I say that we're in model revolution right now, and I think that's what we really are. I mean, things are boiling down to, I mean, the etherists out there are really pushing for, that model. There are, like I said, there are some other models too, but I think there's a more predisposition for people to question even that. I know some people on the progressive side. There's a guy here in Florida. I've talked with him only briefly. He is very much on the progressive side, and they're working on, trying to get, more equality for everyone. And I had mentioned a couple of times that he said, just the way when we turn on the news at night and they tell us, there are Saddam has has weapons of mass destruction, and that there's this gas attack these people are doing. I mean, there's an industrial war machine. We all know that, and people are starting to say, what I'm seeing and what the media, which is owned by what six companies or something, they're all giving us this narrative, and when they tell us this, I'm finding out it's not that. If you look on the news, they don't seem to show the crisis at all. There's a huge crisis here in the United States. They don't talk about it because they're controlled. But what that does is in turn get people to question everything. And I mentioned to this guy, I said, look, we got to get together sometime, because everything you hear on the news and about all these things and, quantum tunneling and all these ideas, and, you can pretty much throw out particle physics all the way back to 1930, and in Big Bang's wrong, relativity's wrong. I mean, the idea of people are more receptive than that than ever. I really have found that out. So I think this idea of the inflection curve, is 89. I'm really starting to see that the reception for this kind of stuff is very, very different. So I agree. So this is part of your saying that, okay, not only am I looking at here are what I think is going to be science going forward, the infinite universe theory and ether, and this is the way gravity works, but you're trying to also predict when this would happen, because of course that's the $64,000 question. It seems to always happen when there is, I don't know. There's just all of a sudden it starts happening. It happens usually pretty quickly. I mean, once you hit a threshold, once that happens, and then let's say the infinite universe theory is acknowledged and to be, the winner of the model revolution age, then that becomes the normal science. Usually those kinds of things happen pretty quickly. I've seen.
Well, that's the idea of a paradigm. It's why I started with the 10 assumptions of science. If you're going to change a paradigm, you have to realize you have to change the underlying assumptions.
Right.
You can't do it any other way.
Yeah.
You can't
Yeah.
do
Yeah.
that.
Yeah.
The math is fine, but it's not going to do anything fun.
Right. Right. Whoops. Frozen there.
You have to have your ducks in a row.
Right.
And you start with, first of all, you have this complaint against the Big Bang, right? You have the complaint. And then the next thing you want to do is to figure out, okay, what are the assumptions that are being made here? Like you did with the neutrino and so on. And you have to say, what are these assumptions? And how do we know what are the correct assumptions?
Right.
And that's why I like Collingwood so much, is because he said every fundamental assumption has an opposite. And you have to choose between the two. And you can't prove which is correct.
Right. Right.
Except by experiment. You might get more evidence in favor of one than the other. And so, and if you can have more than one, it's got to be compatible with all the others.
Right.
And so that's the basis of where we start. And remember, that's what happens when you get a paradigm change, and the economic conditions have to change in such a way too, because that's how people get their food, how they get food, shelter, clothing. So that's what is necessary, and that's why you get tremendous upheavals produce changes in philosophy. You just study it once and you'll see in the past.
Well, that's a good way to end here, but we got about 10 minutes. We have people in the green room. We've been answering. If I know people there, again, if you want to come on, talk with Glenn, if you have a question, wave your hand to me. Unfortunately, we don't. Oh, okay. We'll let Ian on one more time here. So he's been here before, so let me put him on here for him to say something.
How you doing?
Thank you. Very well, thank you. And thanks for having me on. I actually have about a dozen questions, but in view of the time, I'll restrict myself to one point, which is rather a questioning of what I thought I understood coming out. It seems to be a bit trivial, but it's in relation to the spelling of the ether, which you felt strongly about. Now, what I thought came out of this is that you were implying that because Michelson, Morley, and Miller spelt it without the A, they had some conception that it was analogous to the chemical compound ether, and therefore it was quite at variance with what you and others, I'm an etherist, would accept nowadays. Well, for my own part, I wouldn't be as dogmatic. I mean, to me, they're just alternative spellings. They ultimately originate from the Greek word for light bearing. And the modern tendency, I suppose, is where it's pronounced an E, is to get rid of the A. For example, medieval, encyclopedia, Wikipedia. But anyway, whether that's so or not, some people think that keeping the A in, which is your preference, it sort of connotes an ancient mystical ambience, which was postulated by the ancients, which has nothing really to do with modern science. But my main beef is not the spellings, because I'm not dogmatic about these things. To me, they're alternative. But implying that the Michelson, Morley, and Miller ethers, which were really derived from the Maxwellian ether, which to me is quite analogous to the way we're thinking, the way at least I think of. I don't go as far as you do, but I talk about the ether with particular properties. I don't think they were thinking of a sort of a gas, which is, similar to the chemical compound.
Yeah, and of course, I used the wrong spelling for a long time. Early on, I used just the E. I don't know why. I guess I was following the texts on Michelson, Morley, and Miller, and so on. But what I'm doing is trying to make a distinction between the kind of ether that Michelson, Morley was trying to test And what a lot of the regressives say has been proven that ether doesn't exist, which is not the case. It did not. It proved that ether with a small e doesn't exist. In other words, they were looking for this fixed ether outside the Earth. The Earth was traveling through it at 30 kilometers per second. That wasn't found. And the reason it wasn't found is that we actually had ether A, E-T-H-E-R, and that was entrained. And that's why there is a result that increases with altitude, because there's less entrainment as you go further away from the Earth. And that's what Miller was showing, Galeev and so on showed that. And so I like to use that as a pedagogical tool. I don't care if you use E or A or not, but I will, now I'm using it and I put it in my books A, because I'm talking about an ether that's entrained, that is throughout the universe. And they, of course, talk about the small e one as being throughout the universe, but they didn't even think of it as affecting anything on the Earth. It was sort of a particle that when it hit the Earth, it didn't slow down. Well, how could that be? How can something hit something without slowing down? So that's the whole point, and that's my whole shtick on that, and why I changed it to A.
At least you have conceded anyway that Miller, for his part, and probably M&M as well, did conceive of the possibility of an entrained or dragged ether.
Well, except that Michelson Morley was doing their experiment in Cleveland, and the elevation there is very low. And that's why they got a slight change. It's more than zero, okay? They got a slight change, and that a fringe. In other words, that's what they're looking for, light going well with the Earth in the perpendicular. And so they had something. And then as you went higher in altitude, the fringes got bigger and bigger and bigger. And in my book, I show a possibility of doing tests at higher elevations and possibly satellite and so on. And we would get closer to 30 kilometers per second if you went further enough from the Earth.
Okay, thank you very much. I'll leave it at that. Thank you, David.
Yeah, thanks, Ian.
Yeah, I mean, it gets to be a pedantic thing, but in some sense, you really do have to think about history. Just like when I tell people, again about the neutrino, it's like, okay, if you're going to have a particle, I know there's one guy who says the neutrino is like a graviton. I said, just be careful about where you hang your hat and what words you use, because it comes with a lot of baggage. It really does. And
well, history, a lot of people denigrate history. They think, well, it's not important. No, history is the cause for effects.
Yeah, it's in some sense it's the, it's the microcosms of motion of time, right? So because everything that we got to, from
and
once
as we
before.
find out more and more about the universe, remember in Einstein time, we just had the Milky Way and a few fuzzballs out there.
Yeah.
And
how old was the universe in the beginning of the 20th century? It was like millions of years or something.
Yeah, right. So it's ridiculous in comparison to today. And now, of course, the mathematicians are so sure it's 13.8 billion.
Oh,
and of
yeah.
course, every other week or so.
Have you seen him change it? Have you seen him change the decimal point on that page? It is quite amazing. They'll change that the age of the universe by literally 0.2 on the 13.
Well, which is totally ridiculous, but anyway. But with an infinite universe, that isn't going to work.
Yeah,
and it's so amazing how myopic we are. Here we are looking out, and when you look out, up, down, east, west, north, you get the same result, 13.8 billion light years. Yeah. What? And we're at the center of it. Can't be.
Yeah, I know. And it really has to do with the resolution and accuracy of what we're looking at. Every time we get a more powerful telescope, guess what happens? The age of the universe increases.
The probability of us being at the center.
I know.
Is like minuscule, okay? So that's why Einstein is so important, because he talks in general theory, he talks about space-time as being four-dimensional. Okay, right. So now you can wrap it all up in a big ball, still finite. How that can be, I don't know. It's not
Yeah,
my theory.
yeah. I mean,
But that's how we get out of the thing where people say, well, it's improbable that we would be at the center of anything with 2 trillion
yeah,
galaxies
no,
exploding out.
it's true. I mean, you would think that we would see a different. We could actually calculate we're like 3 billion light years away from the center or something like that.
Yeah.
So, but that goes on and on. But listen, I'm going to thank you so much again. It's always stimulating talk with you. Like I said, my father and I are great students of you. I mean, we have some disagreements on very small things. But first of all, I want to say, and of all the ether theories, and I know most all of them because every time a new one comes out and someone comes out, I look at them. You thankfully are addressing a lot of the problems that other etherists are not addressing. You have your explanation of how the gravity works, which I can see totally working. And my guess is somebody like we have Ray Gallucci, and his job is that he loves just taking a theory, take your theory, and he do calculations with the ether and the entrained ether and look at gravity and say, yep, that's a very possible explanation. And then you take a look at ours and he says, nope, it isn't. And then that would be one. Or he'll say, yes, it is. But I think what's the most important is that what you've laid as the foundation, without you and your work, people like myself, my father, we wouldn't even be attempting to try to come up with a model. And I think the foundational shifts are there. I've brought you on many times. I'm hoping that people, especially newer theories, are going to get away from this idea, at least the infinity part. But I want to congratulate you once again for humanity in science, even though you are, one of the great scientists of our age. And whether or not your model of the ether or our model of the particle model, it sort of doesn't really matter because what you've given the world you can't take away. So I want to thank you again so much for giving us your time. I'm sure we're going to find an excuse to get you back here, but I want to say to you from everyone, thanks for this series and for everybody to take a look at the book. Are you planning next year? You're going to be. I'm going to work with you because I know you've been sending me slides, but I'm going to work with you on getting your course ready because sometimes the people close to us don't know how to necessarily teach it the best. So what I'm going to try to do is we're going to be helping you. We're going to be having some meetings. We have a couple of people that are interested in putting courses down, and I think having a course on your work is absolutely necessary. And there's really many parts to it, and doing a course is very different from oftentimes the book. So we look forward to that in 2021.
Sounds like a plan. Like to
Okay,
hear.
well,
Yeah.
oh no, absolutely. So thank you so much. I'm going to bring you down there, and I guess you can go to sleep again. I mean, it was 7 o'clock. You got up early, so thank you for doing that. Okay, you
Yeah.
take care.
Yeah.
All right. So that was Glenn Borchardt again. Amazing mind. Whether you agree with any of that or not, I think it's really hard to argue away with infinity these days, and that's why he calls it infinite universe theory. If he's not getting you to think about infinity, then I don't know who will. But I do want to thank him, and I want to remind people. I know we'll be seeing if we're going to be coming on the next couple weeks because it is the holiday season around the world for many cultures and continents and peoples. So I don't have anything planned and down for the next weeks. I'll talk with Franklin and see if he wants to take that over for a week or two. But I am planning in the new year to be talking to numerous people. It just takes time to get them and their availability. But Alexander Unsker, somebody says I mix him up with Glenn Borchardt. No, I don't. That I don't do. They are very distinct, but he is a wonderful person. If you haven't read Unsker's The Higgs Fake, you should. Every living person who loves science should read it because it reveals the house of cards of the way they go about finding new particles in particle physics. It is scarily bad. If you're an engineer, you will be abhorred by the way they go about doing it. It's just so how do you say, ancestral. They filter out what they want to filter out, and then they let through what they want to let through, and then they call it a Higgs boson, for instance. So you want to check him out. And also we'll be having Nick of Time, who'll be talking about special relativity. I know lots of people talk about that. And so I will let this go and thank again, and all of the people out there who are a member, especially of the CMPS, the Natural Philosophy Society. Please, 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 again, go there, become a member, paying member, $35 or up per year. That's not much, but if we put all our forces together, we are going to have a way then to keep this going. It's very, very important. And if you want to come on or know somebody that wants to come on and talk about something, send me their information and I'll take a look at it. We don't put everything on, but if we feel that's something that's interesting in some way that makes people think and become more critical thinkers, that's great. So, alrighty, folks. Remember, I'm Dave D. Hilser. I'm your no, I'm not your particle model. No, that's my father. I am your science therapist, and you always want to stay thinking, stay critical, and I'm going to take you to the promised land of becoming a critical thinker. All right, guys. Ciao for now.